Okay. So, we left last week with our exploration of the hydrogen atom, right? So, we're gonna take that further now. We know a lot about hydrogen already. Gonna learn some more in the second part today. But first, we're gonna discuss the build-up and how we, in a fairly simple way, can understand the basic structure of the elements in the periodic table. For that, we need to keep some permutations in order today. So we're gonna look at our quantum numbers. Remember, we had the principal quantum number, n, for hydrogen, 1, 2, 3, 4, etc. It could only take integer values. Then we had the one, little l, the orbital, the angular momentum, orbital angular momentum quantum number, which could then go from 0, 1, 2, up to n minus 1. If you don't remember this, go back and look at the solution to the hydrogen atom. And then we had the magnetic associated, the little ml, which could then go from minus L plus 1, so forth, to L minus 1 to L, okay? Now, in our orbital, this was, just to remind you, this was associated with R, this was associated with the theta, and this was associated with our phi coordinate, right? Now, what we mentioned, or what Feynman mentioned, was that we completely neglected that there was also a spin of the electron, or, well, there is an internal angular momentum, also of the electron and the proton, which is often then called spin. Okay? And that goes then by a fourth quantum number, ms. Okay? Now that can only have two values, 1/2 minus 1/2, or if we prefer, spin up, spin down. Yeah? Experimental fact. So, in total now, we have these four, okay? So, before we move on to the periodic table, we gonna first look at the hydrogen atom, the degenerate properties of the energy level of the hydrogen atom, right? Remember, we found that for all L values of the same n, for all L's that has the same principal quantum number, the energies were the same. That is, they were degenerate. Okay? So, how many possible states are there then? Well, if we now stop a little nice table here, and we can say that, okay, in our n equals to 1, then we have 3 more to go, right? So we have our L, we have our ML, and we have our MS now. That's the spin, yeah? So in this case, well, this can only set 0, right? Then this can only be 0, and this can be spin up. But we also have another one, 0, 0, spin down. Okay? So that was easy. That was 2 states. Okay. Now we're going to push it outwards. The principal quantum number 2. Then, of course, well, it can still be in these 2 states, right? So we're going to have these 2. Okay? But of course, the L here can now also take number 1, because it can go up to n minus 1, right? So we can also have this state, 1, and then ml could be -1 there, right? This could spin up, and 1 minus 1 spin down. Oh, I should have, since I put the 2 there, this would be the equivalent, and then we're going to do it like this. Better pedagogically. Okay. So, but of course, this can then also have 0, right? And spin up, 1, 0, and spin down. And since this is m, it can go up to all the way to L, right? So we're going to have I have to add another one as well. 1, 0, spin down. So in total, we have 6 more. So we have 8, okay? For the n equals to 2. And that's all there is. N equals to 3, well, then we can just repeat all of these, right? So we have 8 in total. But then L can also take number 2. So if L has number 2, then ML could be -2, spin up, and then, well, this is just the same but spin down, right? And now we don't have to write out. We see the structure. This could be 0, 1, 1, and 2. And these, of course, are always spin down. So here we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 more. So in total, 18 for n equals to 3. And now you can see the regularity. And you can continue to carry out there to see that the degeneracy of the hydrogen states of principal quantum number n is 2n squared. That's just a permutation that you can carry out here. Okay? Gives 2, then you have 4, gives 8, 3, 9, 18, and so forth. So this will be important for us next week when we move on to try to, okay, so now we have this, but what we also will need in order to do calculations is the distribution of atoms in various states. That is, how many are actually of the atoms in the gas, in the ground state, in the first excited state, and so forth. And we have actually used this already, this result. This is from the Boltzmann distribution, right? We know that the number of particles in some states, call it now the quantum number little n. This is called big N. Again, a mess. We know this is proportional to e to the minus energy divided by kT, right? However, we have to, of course, multiply this then, in this case, by the degeneracy factor of that level. So that's how it will enter also there. It's called then the statistical weight, because we have more places to store the electron, more different states to store the electron in. Okay? So, that's how you can obtain the degeneracies of the various n states, principal quantum number states of hydrogen in this case. All right. So, we can take this away. And we can take this away. All right. Now let's move on to the buildup of the periodic table. So we're going to put in some more protons and electrons. Yeah. We put in another one first there. We put it in the ground state. So we're just going to consider now the ground states of the various elements. Okay? Now, of course, here, in this case, we would have to put 2 neutrons in there as well, right? In that case, you recognize this as atom number 2, right? So this is atom 2, atom number 2, which also goes with the name helium. Yeah. Now, in this case, okay, we can put it in the ground state, yes, and then that ground state is typically denoted by a spectroscopic notation, which has the uses the N and the L. All right. So in this case, yeah, for hydrogen we already did. It was 1, right? And this was in number 0. It's just that it's not used 0. Instead, we put S because you know that the L states 0, 1, 2, 3. They also are called S. P, D, F for sharp, principal, diffuse, fundamental, and then they were out of lines. And like Feynman said, I don't know why, because they're not particularly sharp anyway. We could as well call it spherically symmetric. That was not a good accent, but you know what I mean. Yeah. And then they were out of so to say, lines in the classical spectrum. So then they just kept going in the alphabet. So the next one would be G here, yeah, and then H. But then we had to jump some numbers because some of the letters were already taken for other, like little l. Couldn't use that because it was used already in this orbital quantum. So it's just a mess. But it's how it is. It's better to just learn it and then have it there. Okay. So you know what you're looking at because you see it in all the textbooks, in all the papers. So this is then 1, 0, really, but it's 1s, which is 1, 0, okay? Now, for helium, then we have 1s, 1s. So we have 2 electrons, the first one in 1s, also the second one in 1s. So that's then called 2s squared, and we forget about the parentheses here. We don't need it in this. It's of course not 2, it's 1 s squared, yeah? But we don't use the parentheses, so yeah, well, it should be, right? It's not a squared, it's 1s2. That means that the 2 electrons are in the 1s state, okay? So, then of course, if we go to number 6, so we would put 6 here and we'll put 6 there. Number 6, do we know what that is called? Carbon. Then we have 1s, 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 1s equals to 1s6. Correct? No. Nope. That's not how it works. And that's because of Pauli's exclusion principle. Yeah? And that, I apologize, but that is a thing for your course in, for a dedicated course in quantum mechanics to understand the origin of the Pauli's exclusion principle. We're just going to state it here. And what it states is that for an electron, or more generally, for a fermion, you cannot occupy, 2 electrons cannot occupy the same spin orbital quantum state. Meaning in practice, they cannot have the same set of quantum numbers N, L, ML, MS. Okay. And that's what we need. So now we can start. number 1, hydrogen, right? Where do we put it? Well, we're going to put that at 1, 0, 0, spin up. That was our 1, 0, or 1s state. Helium, number 2. This one is there. The second one we can put at 1, 0, 0, spin down. Since we're only using these two, that's 1s again. So I'm going to put them out here. This is 1s, and this is 1s2, right? But now, when we go to number 3, which is also called lithium, I'm going to draw a line because you see, well, we're filled up here. There's nowhere to go except putting the next electron in the second principal quantum state. It has to be in the second orbital. So the third here is going to be 2, right? 0, 0, spin up. So therefore, the lithium will be 1s2, but then 2s. And then we can go to 4, we can go to 5, and here is number 6, which is our carbon. This one would then be 2, 2, 0, spin down, right? And this one would be 2, 1, minus 1, we can put it in. And this one will be 2, 1, minus 1, spin up, which means that carbon will have 1s squared, 2s squared, and these two, if you look at the first two, they will have 2p squared, or 2, 1 squared. P, like in the principle up there. So, this is the ground state of carbon, okay? Now, furthermore, we can also learn quite a bit from this. And that is that for these two, you see that after we go to helium, you have filled up the first principal quantum number shell, which is also often denoted as a K shell in spectroscopic literature. And now you have to go to the other shell, and by just following through, you can see that the last of this will be number 10. Number 10 is called neon. No, I figured that you had a question. The first two here for carbon, I mean, you can just carry it through all the way, is 1s, 1s, right? 2s, 2s, 2p, 2p. I just put these arrows. Actually, we're only interested in this spectroscopic notation. We're only interested in this. We're not putting the spin down here just yet. Yeah? So then I think it should be like this, okay? Yeah. So the question was if I'm putting these in the right states here. Yeah? So here I just, whether I put this in -1 or in 0, spin up, spin down. This could be spin up, spin up. And this could be 0. You could count it like that, of course. But since I was concerned about the spectroscopic notation with the N and the L, I put it like this, okay? Neon is the 10th, and then we have filled up number 2. That is the N equals to 2 orbital. Number 11 then will have the last electron in N equals to 3, right? Number 11, I always forget which one this is. Is it calcium? Somebody check which one is number 11 and tell me. At least during the break, okay? Yeah? You see, perhaps we should just have them as numbers. That would be easier. The thing here that we will now use one more concept to understand is that this can also tell us about the properties. You know that this helium and neon, they're also called noble gases. Lithium and the unknown number 11 here, they are called alkali metals. And they're called that because of their ionization properties. And we can understand why that is just by keeping this in our head now, and then just using one more simple concept, which will be a qualitative description of this. It's the concept of screening. Okay? So let's just go and see what this concept of screening is. Yes. So, if you have now your helium here, I'm going to skip the neutrons because it's still qualitative. Then we already learned that the electrons here, they're both in the n equals to 1 orbital, right? Okay. So, what does that mean technically? Well, if we go back now to our hydrogenic atom, remember that the ionization potential was 13.6 electron volts divided by n squared. But then actually, if we wanted to do this not just for hydrogen, but what we call hydrogenic, we added the charge squared. And that charge square is the nucleus charge, okay? Now, I should state that for neutral helium, this is not a very good approximation quantitatively at all, because there is an interaction now between these two electrons, which one has to take into account for this case. All right? On the other hand, if we lose one of them, it's a very good approximation, because then we have a hydrogenic atom, only one electron and two, okay? But we can still use it now, and then we'll come back to it, to discuss qualitatively. Because now we see two charges in the middle, right? And n equals to 1, so we can see that this will be on the order of then 13.6 divided by 1 squared times 4, which is much greater than 13.6 electron volt. And this tells you that helium is difficult to ionize. It requires more energies, right? But now what happened when we add lithium here? So we add a 1 here. Where did we have to put the third electron? Well, we had to put it here in the n equals to 2. Now we know from our previous class and the exercise we did, we only calculated the expectation and the most probable value for the n equals to 1 state, right? But in the exercise there were also, you can go on and do that for the n equals to 2 states. We know that on average, they are further away from the nuclei. And this means that if you're now taking the viewpoint of this electron and you're looking at your nuclei charged, you will be screened by these two electrons. They're lying here. It would be better if I put it up here, right? And then you're looking at there, then you're screened, so the effective charge that you see is only 1. So the lithium third electron sees an effective charge of only 1. Right? Imagine yourself, you're here, you're looking at the charge over there, but you have 2 electrons in the way. Yeah? So you see only 1. That's the net charge, 3 minus 2, roughly. Yeah? So the order of magnitude then would be 13.6 electron volt, but now, not 3, but 1. And besides, we're also in the n equals to 2, so we have to take 2, 2. So that's actually then 13.6 electron volts divided by 4, which of course is much smaller than 13.6 electron volts. And that's then why lithium, the first electron, is much easier to get rid of than helium. And this is then why helium is a noble gas and this is an alkali metal. And you can do the same thing for the last element of the principal shell, number 2, that would be 10, neon, would be this property, whereas 11, still unknown to us, would be this. Okay? Yes? 11 is sodium I got from the audience. Thank you very much. It just, I knew that. Yeah. But then again, why do we have to remember so many names? I don't know. All right. And actually, if we carry this thought through, we can understand the basic properties of most of the periodic table by just these 2 things, the Pauli exclusion principle and the screening effect. That's the qualitative example then. Like I said, actually, if we go now and we consider helium, for example, plus, and then we say we have lost one of its electrons, so we have only one left. Yeah? We put it in the ground state, it's n equals to 1, right? But then this formula, this is a true hydrogenic atom, so this will be a very good approximation, and the ionization energy is 13.6 electron volt times c squared, but that's 2 now, so that is 4 times 13.6 divided by 1, that's 40, that's 52, 54.4 electron volt. And that's the ionization state from singly ionized helium, which in spectroscopy you often see denoted by helium plus, meaning that it has lost one of its electron, or helium 2, meaning that it's singly ionized. Helium 1 is neutral helium. Helium 2 is singly ionized. So that's often what you see. And if you look at this ionization age, for example, then you see that and you do the transformation to wavelengths, you will see that it's on the order of 228 angstroms, as compared to hydrogen, which we calculated was at, where was it? 912 angstrom, if I remember right. So this is at shorter wavelengths, higher energies. The thing with this is that this is in a wave band, the extreme ultraviolet, which is just in the middle between the ultraviolet and the high energy X-rays, hence the name, extreme ultraviolet. But it's very difficult to observe. So we almost never see that. So because it's absorbed very efficiently by the Earth's atmosphere. So one would have to, just like the UV, you would have to shoot up your telescopes in orbit and try to observe it. But then it's actually also very easily absorbed by the interstellar medium. The reason is that if you have neutral hydrogen there, and then you come in with these high energy photons, like we already discussed, and what we will come to more when we discuss bound-free transitions, for doing an ionization, you don't have to, like for a bound-bound transition, come in with exactly the same right photon energy. Remember Lyman alpha hydrogen, we had to come in exactly at 1216 angstrom, a little bit for the line broadening, right? But just very tiny, otherwise we can't. For ionization, it doesn't work like that. The likelihood, the cross-section is highest at the edge. After the edge, at lower energies, at higher wavelengths, it just drops to 0. But before the edge, it has a dependence which essentially goes with the energy, the wavelength to the third power. Yeah? And we'll come back to that. But that means that also these high energy photons that are emitted, they can actually absorb or ionize the neutral hydrogen atoms in the interstellar medium very good. Which means that we almost never see this radiation. And this has important consequences also for observations. First of all, the knowledge is in an astronomical concept, mostly theoretical, right? For the the various transitions and stuff that are there. But it also turns, if we want to know about this, what we call ionizing radiation, for example, in the early universe, where it is important in the context of reionization of the universe. Now I'm throwing buzzwords again, and we will come back to that a little bit here, and even more so during the spring, for those of you who take galaxies and cosmology with me then. But we don't see these hard ionizations. We have to use indirect methods, for example, via a helium-2 or helium-plus spectral line that is formed by recombining then electrons, for example, at 1640 angstrom, is one that is very often used for this purpose. Yeah? So this is how we can use this, and then, yeah, this, unfortunately, from an observational standpoint, lies in a region where it's very difficult to observe. But now we know a lot, at least, on how to identify where they are and what they mean. All right, that's what I wanted to say about that.